that we've learned how to find the volumes of different types of prisms, we're going to talk about similarity. Now, this is kind of a throwback to Chapter 8, where we dealt with some similarity issues, and we talked about, side angle, side similarity, and stuff like that, proportions, that whole bit. And the big thing we're going to talk about from that chapter right now, again, is scale factor. So, very simply, if I find the scale factor between two similar solids by finding their corresponding length measurements is A to B, okay, the scale factor is A to B, then the ratio of volumes is going to be A cubed to B cubed. Just like we had previously learned the ratio of areas was A squared to B squared. So again, we have to go back and find that scale factor between the two shapes and then cube that. And we can use that to set up and solve proportions. Now, this is something that was a little bit dicey when we did it back in Chapter 8. In fact, I'm recording this right as we're finishing Chapter 8. And so I know that this is something that's going to be a little bit shaky. So please pay very close attention to what we're doing. All right. I'm going to tell you that they're similar. We are not going to have to prove that the shapes are similar. We'll just go ahead and give you that. What we're going to ask you to do is use that similarity to set up and solve a proportion to find the unknown volume. Because I don't have enough information to find the volume of this particular shape of cylinder B. I don't have enough information to do that. All I know is the radius of it. But what we can do is we can use the fact of similar solids to set up and solve a proportion. First thing you have to do is find the scale factor. The scale factor here is 3 to 6. Or if you prefer 6 to 3, it really doesn't matter. Let's go with 3 to 6. And of course, for scale factor, we always have to reduce. So it's 1 to 2. And we could also express that this way, either as a fraction or as that. So if that's the scale factor, the ratio of volumes has to be 1 cubed to 2 cubed. Well, 1 cubed is 1 times 1 times 1, which is 1. 2 cubed is 2 times 2 times 2, which is 8. So the ratio of volumes is 1 to 8, or if I prefer, 1 to 8. Now that I have that ratio of volumes, I can use that to set up and solve my proportion. And it's really simple. We go 1 over 8, small volume over large volume equals small volume over large volume. My unknown is there, my large volume. I just cross multiply, and cross multiplying here, x times 1 is just x. 8 times 45 is 4 times 90, or 360 pi. And it's context centimeters cubed. Okay? So again, we first found the ratio of volumes. Well, first we found the scale factor. We use that to give us the ratio of volumes, and we use that to set up a proportion. So it's kind of a process here. And it's a process that we did in Chapter 8, so it's a great review for us to do this process. Again, you'll find a lot of things in Chapter 11 make us recall things we did in previous chapters, so it winds up being a really good review for our test. All right, we've done that now with cylinders. Let's have you try it with a couple prisms. Notice they give us the volume of the big prism. They give us the corresponding side lengths, and they tell us they are similar. Okay, so I'm going to kind of walk you through just a little bit. We have to start by finding the scale factor. Okay, and I'm going to leave that to you. We're going to have to then find the ratio of volumes. We're going to find that, and then we're going to set up a proportion. And it's up to you if you want to go small over large, or large over small. That's going to be totally up to you. And solve that proportion to find that area where the volume of prism D here is X. All right? So there you go. I've kind of given you a framework to work with. You try to find that volume. All right, that's enough on similar stuff. Now we're going to move on to just finding volumes of what we call composite figures. In other words, where you have to add and subtract volumes before we can actually find the total volume. So we're going to have to find different pieces, so we have to break the problem down. So here I've got a concrete block. My concrete block isn't solid concrete. It's got the holes in the center. And you've seen concrete blocks before. They make up the walls of the school and lots of different buildings. Okay? It says find the actual volume of concrete in the concrete block. How many square feet of concrete or cubic feet of concrete are needed to make this concrete block? And if you're the manufacturer of concrete blocks, this is a pretty important question. So, what do? Well, what we're going to have to do is come up with a strategy. You got to think of a plan. So before you even begin, make your plan. So plan. Okay, my plan would find the volume of the whole thing. And I notice that the two inside holes to the block are exactly the same dimensions. So I'm going to take the volume of the whole thing, I'm going to subtract 2 times the volume of a hole. And that'll be my total volume. So before I even begin, I have to make sure I have a strategy, know how I'm doing it, and then solve each piece and add and subtract as necessary to find your final answer. So the volume of the whole thing, well, that's a cube, and the volume of the whole thing is going to be base area. I'm going to use this as my base, okay? And of course, we can kind of get the idea that these things are holes that go all the way through, right? All right, my base area is 1.31 times 0.66. Or 0.8646. My height then is 0.66. So my volume is simply base area times height. So that base area times the height is 0.5706 or 0.57 cubic feet. Okay? That's the volume of the entire block as if it were a solid block. Now we got to figure out the volume of a hole. Well, a hole, again, has this base here inside the block. And the dimensions of that base, it's a rectangle, so 0.39 times 0.33. And that's 0.1287. The height is still 0.66 feet. So the volume of one hole is 0.085 feet cubed. So make this 0.570 because that was the 3 decimals, the same thing. Now what do I have to do? I have to take the base area minus 2 times, so 0.570 minus 2 times 0.085 is going to be my total final answer, and it's going to be in feet cubed, so we always can add our context ahead of time. It's 0.570 minus 2 times 0.085 is 0.4 exactly. So I need 4/10 of a cubic foot or 0.4 cubic feet of concrete to make that block. What the holes do, they subtracted off that 0.170. A significant portion of that volume is just air of the total block. Only 0.4 square feet out of 0.57 square feet is actually concrete, or cubic feet, excuse me. So we have to make a plan, we have to execute that plan, and we have to do the math. Find the volume of this solid. So we've got a triangular prism with a rectangular prism out of the center of it, or a square prism. So we're going to start with a plan. Okay, so the volume of the triangle prism, and we have to subtract from that the volume of the square prism, equals total volume. I'm going to help get you started here. We're going to find the volume of the triangle prism first. Now notice that we have markings to indicate it is an equilateral triangle. So the volume of the triangle prism, we got to start by finding the base area. Since it is an equilateral triangle, we can use the equilateral triangle formula. If you don't remember this formula, make sure you go back and check that podcast that I've created, as well as those notes, which you can print out as flashcards, that have our special formulas for areas of special shapes like equilateral triangles and hexagons and that sort of thing. So if you haven't been checking that, that's fine. But assuming that you've checked that, I'm just going to go ahead. The base area here for an equilateral triangle, we do 10 squared times the square root of 3 over 4, which is 100 root 3 over 4, but 100 root 4 over, reduces, so that's 25 root 3 square feet. Okay? The height of the prism, the height here, remember the base is the triangle. The base is not the rectangle. The base is the triangle. That's why we did it that way. The height is 6 feet. So the volume is 6 times 25 is 150 root 3 cubic feet. That's that. Now, I'm going to leave it up to you to find the volume of the square prism, remembering that my base is the square here. And notice that we're indicating each side of the square is 3 feet. So you do this process for the base, and then you come up with a total volume. For the sake of our final answer, I'm going to go ahead and decimally approximate 150 times the square root of 3, even though we could be precise. Let's take that as 259.8. So even though we could be precise for the sake of this problem, we won't be. We'll approximate. And you give me the total volume. All right. It's not really an exit ticket, but it's a great final problem. Assume the leaning tower piece is approximately a cylinder, a height of 55.9 meters, and a diameter of 15.5 meters. Find its volume. This is not a similarity. This is simply a straight up problem. So we've got our cylinder, our leaning tower of Pisa, and it's a cylinder on top too. Okay. We got our height on the outside. What are they giving us? They're giving us the diameter of the base is 15.5 meters. The height of the cylinder is 55.9 meters. You need to find the volume. So again, volume of a cylinder, this is a review problem. Volume equals base area times height. Now, base area here, the base is a circle. So my base area is pi r squared. The radius is not 15.5 though. The radius is half of 15.5, which is 7.75. We have to square that radius times pi, which we're going to approximate because we have decimals in the problem. So when I do that, 7.75 squared times 3.14, that base area is 188.6, and it's meters squared. The height is given at 55.9 meters. So my volume, we multiply the 186.6 times 55.9, and I get 1,054.5 meters cubed. So again, finding the volume of a prism or a cylinder, same basic idea, same formula, base area times height, even though technically a cylinder is not a prism because it has curved sides. All right, that's our lesson for today, and we'll see you in class.